exploring these integrals will be first. Today I will explain in what sense these integrals can be viewed as correlation functions in a four-dimensional supersymmetric gauge theories. That's the BPS side. And later, we will interpret them as correlation functions or conformal blocks of correlation functions. Just put roughly as blocks of correlation functions of two-dimensional conformal field theories. That's the CFT side. And so that will establish the correspondence. And in the meantime, we'll introduce all kinds of interesting concepts like QQ characters, and we'll explore the limits, the relations to algebraic structures, which you're learning in other lecture courses, and the geometric origin from in other modular spaces of which are related to modular spaces of instantons, but they contain them in an intricate way. And so that will be related to the more geometric side, for which you're learning in the course of Professor Okounkov. So that's the general plan. And today, more specifically, I'll review two things. Yellow thing, okay. This is okay. Okay, good. Thank you. So today, let me start with a brief introduction into the following topic: supersymmetric field theory as intersection theory. So some people may say it's a very skewed viewpoint on supersymmetric gauge theory or supersymmetric field theory, but it's in some sense it is both a restriction and a generalization. So it's a useful point of view. So what is intersection theory? It's roughly counting solutions to equations or conditions. And why is it intersection theory? Well, that's because you can interpret, sometimes you can interpret the equations as defining some submanifolds or subvarieties in some algebraic varieties. And if you have impose enough equations, they will have only isolated solutions. So you are counting the number of intersection points of these varieties. Unfortunately, well, the counting problem in general is well, if your ambient space is compact and you can represent these varieties as some homology cycles, then there is a cohomological intersection theory, where you can just compute the intersection index of the corresponding classes in cohomology of the ambient space, and that would be stable under small deformations of your problem, so on the small deformations of your equations, or representatives, in other words, of the cycles. However, in practice, quite often the space on which your equations are defined is not compact. And so you first compactify it by adding some set of ideal points, then compute the corresponding intersection index, and then check whether some of these intersection points happen to sit at the compactification set, and so then you need to subtract that number from the actual number you computed. And whether you can do this in a kind of practical way really depends on how much you add. And so there are different compactifications. So the finer is your compactification, probably the better is your ability to distinguish between the actual contributions and parasitic contributions. But then you have to work harder to actually define this fine compactification. Some of the aspects of this theory we will encounter in our study. So the physics approach to this problem is kind of straightforward. Instead of actually solving the equations, let's say equations, you have some variables x and you impose some equations s equals to 0. Instead of just counting the solutions of these equations, we will be integrating over the ambient space. So this is the space where my variables belong to. So we will be integrating a kind of a smeared version of a delta function. And study this integral. So when the parameter epsilon is small, for any kind of reasonable measure, your integral will be supported near the vanishing locus of your equations. So this is, let's say, s equals 1, s1 equals 0, s2 equals to 0. So this integral somehow will know about the intersection points. It will also know about something. It will also know something about the ways to compactify the space, because that will be partly dictated by the convergence of that integral. Now, the supersymmetric version of this theory is the one in which the integral is set up in such a way that it is actually independent of epsilon. And so then in addition to the naive limit epsilon goes to 0, where you're counting the solutions of the equations s equal to 0, you can potentially benefit from the study of the opposite limit when epsilon goes to infinity, and then the integrand is somehow smeared all over the space x, which might be much easier to work with. And so that's what we will be doing in some examples. There is an additional complication to the story, which is that sometimes we have a group action, so a symmetry group. And so what you're really counting are not the points, but the orbits. And so you're counting the everything what I said, but modulo the action of the group G. So then these integrals are defined in the using the so-called equivariant cohomology, which I will now review. And then there is an additional benefit, which is that you can compute some of these integrals by localization at the fixed points of the action of the symmetry group on the ambient space. So it could be that you have. So this is not a very good picture, because now what I really mean is that each variety of zeros of my sections is actually G invariant. So it is fibered by the action of the group G. And then there are some orbits which are smaller than the other orbits, which may not be, so which need not be on the locus of vanishing sections. And so the integral, suitably defined integral, will actually be localized at the fixed points. So it will be computable by doing some local analysis near the fixed points. Yet it will know there will be some representative of this class, the delta, the Poincare dual to my zero locus of my sections, which will evaluate at this point, and by summing over the fixed points, we will recover the whole information. Yes, yes. So it can be made. So this localization can be understood both in algebraic way and in kind of a practical way. So you can choose a representative of this integral in the given cohomology class, which will be as sharply supported at the fixed point as you wish. But there is also localization in algebraic sense. Okay, so let's try making this a little bit more concrete. To this, I will need I will work maybe with coordinates for a while, as pieces do often. So the slogan of this part of the story is sometimes called the Holy Trinity of fields, equations, and symmetries. This is not like, I mean, this. So fields is what we are given initially. So these are our original variables. So this is the space X. Then we have, in my story, we will be dealing with equations which take values in some vector spaces, more precisely in some vector bundles. So there will be some vector bundle over X. And so the equations are the conditions for vanishing of some section of this vector bundle. So E is a vector bundle. And S is a section. So the equations read S equals to 0. And there is a symmetry G which acts both on X and on the vector bundle. So it's the equivariant vector bundle. And we're interested in counting solutions of these equations modulo the action of the group. So at the output is the moduli space. So it's the set of zeros of the section divided by the action of the group G, and some integrals over the moduli space, some classes. So this is what we want to explore. But of course, if the integral is convergent, it means that in some sense your integrand extends. So there is some way of compactifying this moduli space. So from this definition, M need not be compact, and it's not, almost never is. But since we want to do the integration theory, we might as well try to compactify it. And so, and then we can go back to the original problem and ask whether this compactification can be interpreted as a solution of some maybe modified equations, or maybe the equations which are defined on a somewhat enhanced space, or something else. So whether the compactification is itself a modular space, that's sometimes an interesting question. Okay, so now how are we going to deal with these issues? We will try to set up the appropriate cohomology theory. And so let me start with the usual, let's say, de Rham cohomology. So de Rham complex of X. So I will temporarily introduce some local coordinates on my space X. So this X is the space of fields. And I mentioned in the introduction that we will be talking about the four-dimensional gauge theory. So this X could be the space of, let's say, functions on a four-dimensional compact manifold, or it could be a space of connections on some principal G bundle in a four-dimensional manifold. So X is typically infinite dimensional. But for the moment, let's pretend it is finite dimensional, some finite dimensional manifold with local coordinates xm. And so the differential forms will be the so it's something which we can integrate over some cycles in X. So locally we can write them as products of functions and basic one forms. And it is convenient for the analysis, especially for the infinite dimensional analysis, to not to think of them as the differential forms, but as functions. So these are functions on a supermanifold, which is the tangent bundle to X with a reversed parity of fibers. So the familiar object differential form corresponds to a function, which I will write in this way. So it has some dependence on the ordinary coordinates x. So x are bosonic coordinates, or even. And psi are fermionic, or odd coordinates. So psi's are coordinates on tangent fibers, and x are coordinates on the base manifold x. And so psi's anti-commute, psi m, psi n is negative psi n, psi m. And it's just that, if you like, you can just think of this as a notation for dx, as this formula suggests. But then the usual de Rham differential, so it's an operation on the space of differential forms, becomes a vector field on PTX. Which is odd. So when you apply when you apply this vector field to a function, to an even function, you get an odd function, and vice versa. And d squared is 0 precisely because of the anti-commutation of psi's and commutation of usual derivatives. So that's the familiar story. So my space of fields will actually be not x, but PTX. And so the observables will be some functions of PTX. That is differential forms on x. Was a question? So now I want to incorporate the action of the symmetry group. And so what we are doing is called the Cartan model of equivariant cohomology. So topologies, so it was introduced as a model of the following topological construction. So for compact group G, for compact Lie group G, there is a space which is called EG, which is a contractible topological space with free G action, and BG is a quotient. So this is called the classifying space. What does it classify? It classifies G bundles. So if you have any topological space Y and the principal G bundle, there is a unique up to homotopy map of Y into BG such that this bundle is induced from the universal bundle EG over BG. So typically, when G is small, is compact and is kind of reasonably small, BG is pretty big. So for example, if G is the group U1, a circle, then BG is the infinite projective space. And EG is the infinite dimensional sphere, which is defined as the set of sequences of complex numbers which are finite, so that at some point they become 0. But you don't know in advance at which point they become 0, such that the sum of squares is equal to 1. And so the group U1 acts on this space by multiplying all z's by a face. And this action is free, meaning there are no fixed points. So there is always, so at least one of the z's cannot be equal to 0 because of this condition. And so since one of the z's is not 0, then multiplying by a face will change it to a different complex number. So this is obviously a free action, and it's contractible because so this sphere, you should think of it as a kind of a limit of a union of circle embedded into a 2-sphere as an equator, and then embedded in a 3-sphere as a next equator, and so on and so forth. And when you think about this picture, you can contract the circle along the 2-sphere along the 3-sphere, and so on. And so you can. This is related to the Hilbert Hotel construction when you push your you push your guests to the next room. Right. So that's the simplest example. If your group is a unitary group UK, then BG would be the Grassmannian of k-dimensional planes in infinite dimensional space. So that's a limit of the space that Andrei has told you about. So it will correspond to this queer variety with the infinite dimensional framing space. Right. So now, if you have any space X with a G action, and you'd like to study a quotient X mod G, even said theoretically, this may not be a good idea because G, so X is a union of orbits, but there are orbits of different dimension because G doesn't have to act freely. And so instead of dealing with a kind of singular space, you can replace it by something on which the group G acts freely. yet topologically you don't change much. So you multiply X by a contractible space, and now make the group G act on this space diagonally. So it acts on X the way it used to act, and it acts on EG the way it's supposed to act by definition of EG. So now that space is well defined, and you can study its cohomology. So this is the topological definition of equivariant cohomology of X. But then, for practical purposes, it's not a very good definition because, as we saw already in the first simplest example of U1, EG is an infinite dimensional space. So if you like to represent cohomology, let's say by de Rham cohomology, then your problem has become infinitely more complicated because of the infinite dimensionality of EG. Luckily, you don't need much of differential forms on EG. It turns out that there is some minimal construction which effectively replaces the differential forms on EG by the so-called Weyl complex, which is similar to functions of PTX, where X is now the Lie algebra of the group G. And then you can further simplify your life by observing that, well, in a good situation, so if, okay, let me start. If G acts freely on X, then differential forms on the quotient of X mod G, which is defined, can be realized. So you can pull them back using the projection from X to the quotient. You can take the pullback of the forms to X. And so, so the differential forms on the quotient sit inside the differential forms on X as the subspace of basic forms. So these are forms which obey two conditions. Okay, let me say it in the following way. So inside we have G basic forms, which are isomorphic, the forms on the quotient. And so the G basic forms are the forms which are annihilated by the operations of contraction with vector fields generating the action of G. So V are vector fields on X, which are generators of the G action. So they are infinitesimal G transformations. Okay, where is my horizon? So is it here? Okay, at least. Okay, let me write something on the whiteboard just for completeness. Okay, to summarize. So first of all, size under commute. Basic forms. So this is the kernel of So these are forms which are annihilated by the operation of contraction with vector fields and operation of Lie derivatives. Now, I mentioned a new operation. it is instructive to express it also in the language of superfunctions. So the contraction with the vector field has a similar expression, except that now the roles of the bosons and fermions are switched. So this is Vm of x d by d psi. So remind you that the operation of contraction with vector field decreases the degree of differential form. So it eats up one of the dx's and substitutes it with the corresponding component of the vector field. And then the Lie derivative is it's a bosonic even operation. So this is odd, just as d is odd, and iv squared is also equals to 0. But the Lie derivative is the anticommutator of d and iv, and it has, so we can compute now this explicitly. There is a naive derivative part when you just differentiate all the coefficient functions of a differential form with respect to the vector field as if they were functions. But there is also another term where you do something with the dx part. So you roughly differentiate x under the d sign, and then you apply d. So that's what happens. So the basic forms are the forms which are annihilated both by iv and by the Lie derivative. And so these are the forms which are, if the form is annihilated, omega is such that iv omega is equal to 0 and Lie derivative of omega equals to 0, then there exists a form on the quotient, ordinary quotient, such that omega is the pullback of that form, where pi is a projection to the space of quotients. And so when we want to integrate over the quotient space, it's the same thing as to learn how to integrate the basic forms over x. Of course, you cannot literally integrate the basic form over x because it cannot be a form of top degree simply because it is annihilated by lots of vector fields. So so somehow you need to okay, this is also below the, so somehow you need to supply with some additional form. So mu should be a kind of a volume form along G orbits. And it should be such that it basically just eats up the volume of the group. It doesn't do anything else. So and so then you can multiply it by the basic form and integrate over the total space. So we will give a construction of such form using some auxiliary variables, which will enhance our set of fields. But for the moment, let me deal with the other problem. The other problem is that typically the quotient x mod g does not exist. And so we don't have the space of basic forms on x, but we can discuss the space of basic forms on x cross EG. And so that's can be done. Well, I will not go through the construction because I will not use much of it. Let me just say that it have basic forms. It means that they are killed by IV. So not yet. Actually, no. Okay. Basic forms. So basic forms on X cross EG can be modeled on the following space. We take differential forms on X, as before. We multiply them by functions on the Lie algebra of my group G. And we impose the condition of G invariance. In other words, the way I like to think of this is these are G equivariant functions valued in differential forms on X. So in other words, these are objects of the following kind. So alpha. So alpha is a function on the Lie algebra. So for any element of the Lie algebra of G, alpha of sigma. So for any element sigma of the Lie algebra of G, alpha of sigma is a differential form. And it is required to be G equivariant, meaning that if I conjugate, so this is really just the adjoint action of the group on Lie algebra. So the conjugation of sigma by the element of the Lie group is the same thing as acting by G on X. So this is what equivariance mean. What it means. And the grading, yes. The grading is that so the ordinary differential forms were graded. So we had grading. So grading of differential forms, for which, for example, this form has degree k, is the same thing as the U1 action on PTX. And so that action is generated by another vector field, which is even. Let's call it U, which is simply psi d by d psi. So that was so that's the ordinary differential. That's the ordinary grading of differential forms. And now, on this space of equivariant forms, so this is called, by definition, G equivariant differential forms on X. The grading is now modified. So U is now psi d by d psi plus twice sigma d by d sigma. So the functions, the homogeneous functions of sigma of degree L have, in addition to the differential form degree, they have degree 2L. The reason for that choice is that sigma represents the curvature of some well, if you have a differential geometric construction of the space EG, then it will actually come with a metric from which you can compute, you can find a connection on the G bundle of EG over BG. And so that connection will have a curvature, and that curvature is represented by sigma. So the model which I'm talking about really just takes of all differential forms which you could define on BG. You take only those which are built using the curvature of that connection. And I mean, the curvature is not well defined on BG, but it is well defined on EG as a G equivalent 2 form, and that's what sigma is. So that's the G equivalence condition. Right. So now our space of fields has been enhanced. Has just been enhanced to be the PTX cross the Lie algebra, a copy of the Lie algebra. So I define now a bosonic, an odd vector field, which we call grading. And there's also an odd vector field, which squares to 0, which is a generalization of de Rham differential, which is the sum of the de Rham differential on X plus the contraction of the vector field corresponding to sigma. So in components, this is psi d by dx plus sigma, so v of sigma m d by d psi m. So v of sigma, so remember, so here I should have probably better denoted by v a linear map from, so let me do it slightly different way. So v of sigma intersection over all sigmas in the Lie algebra. And so v here is a map homomorphism of the Lie algebra of G to vector fields on X. So homomorphism means that the commutator of the vector fields as vector fields is equal to the v vector field corresponding to the commutator. So v of sigma 1, v of sigma 2, the commutator computed in X is equal to v of sigma 1, sigma 2. So it's, if you like, this is some system of first order partial differential equations on vector fields. Yeah. Okay? So, what we can integrate now are the equivalently closed differential forms. And so this Q, this notation, so Q squares to 0. And why is that? That's the consequence of all these relations which I wrote and the conditions that alphas should be G equivalent. So when you compute the square of Q, the first term squares to 0 as before. The second term squares to 0 by this condition. And then there is a cross term, which is really just the Lie derivative of v with respect to v sigma. And that's 0 because when you substitute in here g, which is exponential of sigma, in this part you get nothing because g, because for g of the form e to the t sigma, g star of alpha is equal to alpha. Because for g of this form, this expression is equal to sigma itself. And so you just get, and I should remind you that what is a Lie derivative? So Lie derivative with respect to vector field u of a differential form, this is an infinitesimal version of a diffeomorphism applied to differential form. So this is e to the t u star of alpha. Well, this sigma is substituted already, so what I'm writing here, think of this as it's a vector field on this supermanifold. So sigma is just a coordinate, it's a linear coordinate on the G factor. So this vector field is linear as far as this factor is concerned. It does not differentiate in this direction, it only differentiates here, but the way it differentiates depends linearly on where you are here. And so the remarkable thing is that this Q is actually a part, it is a part of physical supersymmetry. So if you open your textbook on actually n equals 2 supersymmetry in 4 dimensions, you will find many supercharges, so there will be several generators of supersymmetry. One of them will have this form where X will be the space of connections on some G bundle of a 4 manifold. Perhaps later on in these lectures we will discuss the meaning of other supersymmetries, but for today's purposes, this one supercharge will be enough. So this Q is sometimes called the supercharge. It's called, sometimes it's called a scalar supersymmetry. Sometimes it's called topological supersymmetry. Different people like different names, but and it is also just the equivariant differential, equivariant de Rham differential. That's probably the most accurate name. Okay, so so that takes care. So this part of the story takes care of fields and symmetries, but there are also equations. So we ultimately we don't want to study the space X. X is somehow nice space, with, but the complications and interesting dynamics, whatever it means, will come from imposing some equations. And so we need actually an extra multiplet. Well, sorry, I should have said that to realize this construction, to realize to be able to integrate along the orbits of the group G, or more precisely, if you want to, if you are in a situation where the quotient exists, how do you recognize now the basic forms inside the equivariant forms? So there are two things we need to discuss, and they're related. Well, let me just give you the answer. It turns out that it is beneficial to multiply this by yet another. Well, this time really contractible space. It's just so the Lie algebra, which is a vector space, and we take its we take differential forms on the Lie algebra, or in the super language, we now take the tangent bundle to the Lie algebra with the inverted parity. So it is just a first seems like a redundant procedure, but we will see immediately that it will help us in realizing this mu form. So this is to be able to integrate. So the notation, typically the notation for coordinates on that space are sigma bar and eta. So sigma bar is it's an even coordinate on the Lie algebra, and eta is like a differential. So the notation suggests that maybe we should think of sigma as a holomorphic variable and sigma bar as a conjugate, and then eta as the 0, 1 form. So in some sense, the functions on that space can be identified with Dolbeau complex on the complexified Lie algebra. For analysis, that's sometimes useful point of view, but sometimes it is better to view sigma and sigma bar as independent real variables. Both points of view are useful, and it's like it has to do with different choices of integration contours for the integrals which I'm going to consider. So so now I will extend my operator Q by in a trivial fashion. So Q now will be dx plus IV sigma plus d bar of sigma plus the contraction with the adjoint vector field. So it's a contraction with vector field sigma, sigma bar, d by d sigma bar. So in components, this is psi d by dx. I will skip now the coordinate labels, plus v of sigma d by d psi, plus eta d by d sigma bar, plus commutator sigma sigma bar d by d eta. So this starts looking like a textbook in supersymmetry where you have lots of formulas, many components. But in reality, what this is, I just replaced. I should have said that instead of writing this way, I could have said that this is the standard covariant differential on now PTX cross G. So I just what I did, I extended my space, my original space, X by a copy of Lie algebra. This bracket, it's just it's a commutator. So it's a Lie algebra commutator. It's a G. Sigma and sigma bar. Well, these are linear functions. Yes. So these are just, well, here, if I write it this way, sigma is just an element of Lie algebra. And so so d by d sigma bar is just, well, derivative, linear derivative along the Lie algebra.
Can you just write it out in coordinates so there's no ambiguity?
Okay, so if you introduce, so let's say sigma capital A and sigma bar capital A. So A goes from 1 to the dimension of the Lie group. So these are the linear coordinates on the Lie algebra. Then, and so there is also eta. So then eta, the confusing part is eta d by d sigma bar A plus F, I guess, lower A, B, C, upper C, sigma A, sigma bar B, d by d eta C. How's that? That's this part. I don't. Well, I don't want to write using bracket. Sigmas are in G, yes. Because see, you should have asked before because I was exponentiating sigma. No, sigma is it's an element. So you see here I'm evaluating V on sigma.
So sigma is the tautological map from the supermanifold.
So for me, sigma and sigma bar, they're both in the Lie algebra. They're vectors in the vector space. Okay.
Is this kind of the way to talk about the Cazul complex?
We're not there yet. We'll get the Cazul complex when we'll talk about equations. Because for the moment, there are no equations. They're only.
But when you added this TG, this is what going to do?
No, it's so. Well, for me, it looks like just a slight enhancement of the space itself. It's that sometimes when you have a space with the action of the group, it's useful to multiply by some standard spaces with group action so that you're slightly you make the action freer. This differential forms on x cross little g, literally. Yes. This is differential. So that part plus that part, this is just a differential, usual Durand differential on x cross g, and that part plus that part is the equivariant extension of the differential, where I'm acting on the Lie algebra by in adjoint representation. Yes, Ezra.
Q was defined, well, not defined, but we were only using it on invariant forms.
Right.
What's the analog?
Yes, absolutely. It should also be also invariant. Also invariant. Yes, also invariant.
Just under G.
Invariant under G. Only.
This has square zero on invariant forms,
Yes. Yes.
where G acts on eta and sigma bar.
Yes. So G acts on eta bar and C and eta in adjoint representation. Yes, yes. So we're going to we allow now we will allow forms to have this additional G dependence, and this will be beneficial for constructing this mu guy. Okay, and so how it is beneficial? Well, very simply, if your action is free, then there is a so-called connection form. So if G action on X is free, then there exists a connection form. So it's a form, it's one form on X valued in the Lie algebra. Such that I want to say that IV of sigma contracted with theta gives sigma. And it is also invariant. So now using that form, we can do the following. Let's define, so I'll define mu as exponential of eta I probably want to use some, so at this point I assume that there is an invariant bilinear form on the Lie algebra. So assume invariant form on the Lie algebra exists. So it exists if it is a compact Lie algebra of compact group. So then I'll take the contraction of eta with theta plus maybe with times I, plus sigma bar, and then sigma plus the curvature of theta. So curvature. So what this form does, well, you can check that this is Q closed. Using all these relations and all invariances. So now, what's so good about this form is that now if I integrate over x, so pt, x cross g, something, so omega, which is any equivalently closed form omega times mu. So part of this integration involves the Bayesian integration over etas. And so that will, so it's, okay, in detail, so this is dx d psi, d sigma bar d eta, and then d sigma. Sorry, not yet d sigma. So this is not yet, we're not yet integrating over sigma. So this is times omega times mu. And let me, for the moment, assume that omega does not contain any etas. So let's assume that omega came from the old, from the smaller complex where we only had ptx cross g. Then the only way to saturate the integral over the theta variables is to bring down as many thetas as possible, and you need to bring all of them, namely the dimension of g amount of those. And now theta, thanks to this condition, so it's one form which has at least one leg along the action of along the orbit of the g action of the g group. Now, little omega being the equivariant form, and sort of, if you should think of omega as of the basic form. So the basic forms don't have any legs along the g group action. And so the part which will take care of the orbits of g inside x will come precisely from expanding this exponential in thetas. And so you take the product of thetas, the top degree product of thetas. Thanks to this condition, they will basically give you the volume form on the Lie group G. So if we just normalize my measure by dividing by the volume of the group, that will produce something which you can really compare to the integral of the original basic form of the form living on the quotient, integrate over the quotient. So that's the construction of how to, which allows you to represent the integrals over complicated spaces, which are the quotients, in terms of the simpler integrals over the bigger spaces, larger spaces, but with a simpler structure, at the expense of multiplying by this mu form, which has this exponential form. Now, the interesting feature of this construction is that even if the action of group G is not free, so you can still use this construction by relaxing the condition on the form theta. You don't really need theta to have this property. You may relax this condition to, for example, the condition that the contraction of theta with the vector fields corresponding to the g action is non-degenerate almost everywhere. So it's not equal to sigma, but almost equals to sigma up to a non-degenerate operator. And that will still give you something which you will be able to integrate. And we will now see more explicit examples of that. For example, you can use the following object. Suppose X has a G-invariant metric. Little g. And so if the group is compact, you always have G-invariant metric because you can take any metric and then average over the action of the component group. So then you can take so now I'm assuming that the Lie algebra has an invariant form, and the space X has a G-invariant metric. So then take for theta the contraction of G with V. So okay, so this notation might be a little bit confusing. So here I'm identifying the Lie algebra with its dual, and so this is where the Lie algebra goes, and this is where the vector fields in X go. So theta should be one form on X, and so that's the input for the one form. That's what you put the vector fields in X. And theta should be valued in the Lie algebra, but now I'm making it valued in the dual Lie algebra. And so that's the input for the Lie algebra. So this guy will not obey this condition. Instead, when you substitute vector field, you will get something like a metric on the Lie algebra embedded in the vector fields in X. And so if this is almost, if my vector fields are only have isolated zeros, that's good enough for my forms to be to define a good integrand for my story. Yes.
So this is like a polynomial or worse in sigma bar, and yet you're integrating over sigma bar.
Oh, this is actually no. This is worse. This is exponential sigma bar.
Yeah.
And so
Because sigma plus f is sort of.
but sigma is not. Sigma is
Exactly, but if I fix the degree of sigma, then
well. You will have.
in any case, it's bad.
Well, it's not that bad. So the question is, so it's either depending on how I choose my polarization. So whether I treat sigma and sigma bar as both real or as complex conjugates, this integral will produce something like. So I should have continued this more precisely. So yeah, with the place with this more room. So. Mind you that so okay, I should this is not correct. Sorry, thank you, Ezra. So this has not been integrated over sigma yet. So the good so Ezra is worried that I'm doing integrals like sigma bar sigma over the sigma bar, which looks like a delta function of sigma. So it's a kind of singular object, but I will get rid of sigma as well. So the good thing is that if you do that integral, this is like 1. So it's quite all right. And if you choose a different counter, so it depends on the counter. So for real counter, and if you can do another counter and then get it look like the sigma over sigma, and still get it 1 by residues or something like that. So in this case, at the problem for the problem at hand, the integral over sigma bar. So the original integral, we had omega, which was, after all, a function of sigma valued in differential forms on X. and then we integrate it over Lie algebra, this mu object. So what it gives, it will give me an integral of omega of sigma, and then I want to integrate over sigma. So that's what I want to say. So I want to divide by the volume of the group and multiply by the Haar measure on the group evaluated at identity. So it gives me a measure on the Lie algebra. So that will give me the integral over sigma, and I will have something like sigma plus f in denominator over x mod, almost mod g. So this is assuming that the mu part literally has eaten up the volume of the group. And so that will give me the integral over the quotient, if it exists, of my original equivariant form, where I substituted, instead of sigma, I substituted the curvature of the connection form. And so what it tells me is that if my original equivariant form was just a basic form, then I don't gain much, because basic form only depends on x, doesn't depend on sigma. So I will get what I wanted to get, the integral of the basic form, the integral over the integral over of the form which is pulled back from the quotient over the quotient. But the advantage is that now we recognize that if in doing the analysis of equivariant cohomology, of the cohomology of this operator Q on the space of x, sigma, and psi, we found an interesting class which depends on sigma, that sigma will be the curvature of the connection on the principal bundle x over x mod g. So in particular, you could start here with the silly object, which is just a polynomial of sigma, has no x or psi dependence. So we should. Yes. Well, that's why I had minus f here. Maybe it's unfortunate notation, but I'm used to it. So sigma is like minus. So what I want to say is that you see, so my operator Q squares to 0. So of course the first order of business is to find out what is the cohomology of this operator.
So this step you just wrote here, this is going to be a continuation of that line?
Yes. Well, not continue. So I'm taking this and integrating it further over sigma, because here sigma was fixed.
So that's what the first integrand there is, d.
Right. That's.
The second integrand is going to maybe different from what you have there, but that's supposed to be the result.
Well, you see, the second is so.
No, the second integrand in the first on the left-hand side of the equality there.
Okay. So when I was at this blackboard, I explained that when you integrate over eta, you generate the volume of the group. You generate the volume form along the orbits of the g action. And that's what you need to make this integral meaningful, because omega being a basic form doesn't have, cannot be integrated along the g group action, because it vanished, sorry, not here, but it vanished. Then Ezra started asking me about the eta bar integral, and I just did this integral on the spot by saying that this is an integral of exponential of a linear function. So it gives you either a delta function, but I don't like delta functions where you substitute differential forms. Instead of, I represented this as an integral from 0 to infinity, and this is what I got. So this is an object which you can expand. So it's a meromorphic differential form on sigma. F being the curvature, it's a 2 form, so you should expand it in power series, for finite dimensional spaces, this series will terminate at some point. So we'll get the form of with some pole of bounded degree. And then if you just naively compute this integral over sigma by residues, that's what it will give you. It will just replace the argument of the equivariant form, which is usually assumed to be a polynomial in sigma, by negative curvature, by the value of the residue. And then I was proceeded by saying that well, it's a good news because an example of cohomology or potential cohomology, so something which is Q closed, of Q are invariant polynomials on the Lie algebra. So any invariant polynomial obeys all the conditions we imposed. So it's a function of sigma x psi sigma bar eta, which just happens to be a function of sigma only, which is G invariant. That's the only condition. And so therefore, since my operator Q does not differentiate with respect to sigma, it is obviously Q closed. And now you can ask, what will you be computing if you substitute this polynomial in place of omega? Well, the answer is that you will be computing the integral of the quotient of one of the characteristic classes of the principal G bundle, where you just substitute in this polynomial the curvature of the bundle of x over x mod g. The curvature is not itself; it's not a form on the quotient, but invariant polynomial of the curvature is a very differential form of the quotient, and it's moreover it's a closed differential form, and so that's what you will get. So that's how you recover the integration theory of the quotient space from the integration theory of the ambient space. But now, if the quotient does not exist, what do you get? It's still interesting to see what can you get, and that's where you can start playing with different representatives of this form theta. I should have said that this is actually what I've written here is secretly Q exact. So it's 1 plus, so it's Q applied to sigma bar theta. Now, there is one caveat here. So naively, you can naively say that, well, it's exponential of Q exact, so it's 1 plus Q exact. Therefore, having mu is the same thing as having 1, which means nothing. But this is not so innocent a manipulation because the space, the underlying space over which you integrate, namely the Lie algebra, is non-compact. And so over non-compact spaces, you cannot freely neglect Q exact terms. You should be mindful of what happens at infinity. And so you're allowed to modify the expression under the sign of Q if this modification doesn't change the convergence of your integral. And so replacing this by 0 will definitely change the convergence of the integral. So that's not allowed. But multiplying it by 2 is perfectly allowed. And you can actually see it with your naked eye. If you multiply the whole expression by 2, so when you integrate over etas, you will get 2 to the power number of terms here. But then when you integrate over sigma bars, you will get the same factors of 2 in the denominator, so they will cancel. Okay, so I'm being a little sloppy. So when I integrate over, it's okay. I should have stated it. This doesn't work as the base. Okay, so the integral over pt z for any variety of a function times the canonical Bayesian measure. So Bayesian means that you have, so pt, so for every variable on the z space, you have the corresponding variable on the tangent space with opposite parity. And so there is a canonical measure, which is the product of differentials.
Maybe it would help if you just repeated. So you were going to write down this sort of.
Let me just finish this. Sorry. So let me try to finish one sentence. So this is the same thing as the integral over z of f u is a differential form. Now, so this here f is a function on ptz, and here f is a differential form on z. So sometimes I'm using this notation interchangeably. So if I don't, so if I write integral over the bosonic space, it's the same. It is the same thing as integration over the pt of this viewed as a function, and then multiplied by the Bayesian measure. Yes. Now, what was your question?
Maybe you could just so you're doing an integral over x times g, or by tx times g, whichever, and then there's also a further integral over g. Right. I mean, because
So this further integral over the algebra.
Yeah.
The algebra.
Maybe it would help if you sort of just repeated, because repeated what is like the final answer ended up being for the model of equivariant forms.
Okay. So here, all right. So okay, to be consistent with my notation. So here I'm integrating over pt of x cross g, but here I'm integrating only over the ordinary space g. So there is no pt part. So here I have to specify the measure, and that's the measure which is defined canonically for compactly groups. Namely, you take a Haar measure normalized to 1 on the group, and then evaluate it at the tangent plane at unity. So that gives you a measure on the Lie algebra. That's the measure which I'm using here.
Yes. If the quotient exists, if the quotient x mod g exists, and omega is Q closed.
So here I took an example of a Q-closed form, which was just a polynomial of sigma. Doesn't know, at first sight doesn't know about x at all. So I'm just going through this construction at the example of omega, which is a polynomial of sigma.
Yeah, I just want to check if omega is anything that's Q closed, is that an x mod g exists? Is that equation literally true? You have x mod g in quotation marks there. But like
Okay, so if it exists, then this is literally true. And then you can write not only the polynomial of sigma, you can write any equivariantly closed form. Just at the last step, you will replace the sigma component of the equivariant closed form by negative curvature of the band. So that's the claim. So then it will be slightly more confusing because you will have a mixture of degrees of differential forms. Omega itself may have some differential component, and then it has an argument which is sigma, which is being replaced by the curvature, becomes also a 2-form. But that's consistent. That's why we have this strange grading where every degree of sigma counted for 2. That's because sigma is secretly the curvature. Okay, who's watching the time? How much time do I get? Okay. 5 minutes. 9 minutes. Okay, good. Okay, guys, I need to go to equations, and I'll probably discuss the general theory of equations next time. I need to talk about specific equations for specific space of fields, which we will be dealing with. And that's so my interest in these lectures will be in the modular spaces of instantons. So these are solutions of partial differential equations on gauge fields living on 4 manifolds, and the 4 manifolds So gauge theories on four manifolds. And four manifolds would be the Euclidean space R4, and its various compactifications. So it can be compactified by adding one point. It can be compactified by adding two-dimensional sphere at infinity. And also, we will be considering quotients of Euclidean space by various discrete groups, the discrete subgroups of the group SU2. So in this presentation, when you fix a complex structure on R4, identify it with a two-dimensional complex plane, we will be interested in quotients by the group, by the finite subgroups of the SU2 acting on C2 is in two-dimensional presentation. So it's an example of, so gamma can be, for example, group Z mod L, where it just multiplies the two coordinates by two opposite phases. Or it could be a dihedral subgroup, which in addition to these multiplications also contains a kind of rotation. So this is the A type, D type, so semi-direct product of this. I think we need even L in this case. So Z2 is Z4. So. Right, this is a rotation by 90 degrees, complexified rotation. And there is also an E type, which are the double covers of the symmetry groups of Platonic solids, tetrahedron, icosahedron, and octahedron. Right. So now these spaces also allow desingularization. So this is the quotient is a singular space, but they can be desingularized. And the most efficient way of describing this desingularization is using the Quiver varieties. So that's you will probably learn in the lectures by Professor Okounkov. If not, we will review it quickly. And now we will be interested not on the spaces per se, but on the spaces of solutions of partial differential equations defined over these spaces. And so what are these equations? Yes. So the space itself is a quiver variety. The quiver in question is built using the representation theory of gamma. And the ADE classification is Mackay correspondence, indeed. So the corresponding quivers happen to be the Dynkin diagrams of affine AD or E type Lie algebras. So you fix a principal G bundle over the form manifold, or rather its compactification, one of these compactifications. So this space also has a compactification of a similar type. And then we can see, so the space X, which we discussed so far, will be the space of all connections on this principal bundle. And then the group G, I will have a different notation, so this will be the group of gauge transformations. So these are sections of the adjoint. So it's a bundle with the fiber G, but it's not a principal bundle, but rather the one which is associated with the principal bundle with the help of the adjoint representation, adjoint action of the group on itself. Actually, what I mean by that, I mean the transformations, so the group of gauge transformations on the compactification which vanish, so which tend to 1 at infinity. So these are so-called framed, so these are framed gauge transformations. In local coordinates, so locally a connection is a G-valued 1 form, so the gauge transformation acts in the following famous fashion. So the G which enters this formula is required to approach 1 sufficiently fast as x goes to infinity. So infinity means the wave, so to the compactification set. Okay, and finally, so the equations, so these are my fields. So these are fields. These are my symmetries. And my equations will be simply that the curvature, so the curvature of this connection should be anti-self dual. So this is the Hodge star operation. It acts on 2 forms, on M to themselves, and squares to 1 for Riemannian metric. So it has 2 eigenspaces, the eigenspace of self-dual 2 forms and anti-self-dual 2 forms. And what we want, the equation which we impose, is that the curvature of our connection is anti-self-dual. And so that produces the first moduli space. So it's a modular space which is attached to the principal bundle P, which is a space of solutions. So it's a space of connections whose curvature is anti-self-dual, divided by the group of framed gauge transformations. This is called framed. Now that would be, well, it's a very abstract space, and would be very difficult to talk about unless we had some model of the space, some construction, which fortunately we do have, and that's again is given by some quiver data for the for groups G of classical type, so for the unitary orthogonal symplectic groups. So I will be talking about unitary groups from now on. And for these groups, there is a nice ADHM construction. Atiyah, Drinfield, Hitchin, Manin. So my notation will be slightly different from notations of Andrei, because so I will have, in my lectures, I will have two types of quiver varieties. And so for one type, I will have probably the same notation, and for the type which I'm presenting now, my notation will be slightly different. So my gauge group will be, for today, will be the unitary group, UN. And now the bundles, so G bundles on S4 are classified topologically by an integer k. So what this integer is that, so if you take the four-dimensional sphere and view it as glued out of two half spheres along this three-sphere equator, so you can trivialize your bundle over the north and south poles. And so then over the equator, you have now two trivializations which differ by a fiber map. And so P d plus is a map. There is a map from P d plus to d minus, which is a map of the so over the intersection d plus d minus, which is homotopic to S3. And so this isomorphism is classified by the map of S3 into the group. And that map represents a class in the third homotopy group of G, which is isomorphic to Z. That's the number. Okay. Now a little bit of analysis. So if you connection extends to the compactification on the sphere, so you can compute.
So n is greater than equal to 2.
Yes, you're right. So this is for n is greater than equal to 2. Good point, because we will be talking about n equals 1 as well. So so trace here means the trace in the n-dimensional representation. Now the curvature, it's a two-form locally valued in the Lie algebra of the group. The Lie algebra of the group of unitary matrices is the space of anti-Hermitian matrices. So it's the same thing as I times Hermitian matrices. And so trace of a square of anti-Hermitian matrix is a negative definite quadratic form. So if I put minus here, then this is going to be something non-negative. And now if my curvature obeys this equation, then this is equal to integral of trace f wedge f. And that's, you can compute up to some factors of 8 pi squared. This is equal to the number k. So my instantons only exist for k which is non-negative. For k negative, this space will be empty. We need to consider anti-instantons, but we will not do that. And so, so from now on, my number k will be non-negative. And so now we can categorify these two numbers, namely introduce vector spaces of corresponding dimensions. Signal? Minus 10 minutes? Okay. Well, you had already quiver construction There's always tomorrow. Okay, not always, but today there is tomorrow. All right, so we'll start tomorrow with this modular space, MKM. Okay, see you tomorrow. Unfortunately, probably means that most of my problems cannot be even posed for. But, well,